If sonar can only penetrate shallow depths, and the experts know that's true, then how are they seeing what lies beneath the pyramid?
They are not showing their techniques carefully. They are not.
Just because the discovery was announced poorly doesn't mean the discovery itself is false.
Bullshit. It is total bullshit.
Take the techniques that they said and show it to any scientist. No one can tell you this is accurate.
On March 16, 2025, a press conference was held in Italy to announce the discovery that, by now, is no longer unfamiliar to many. Beneath the Pyramid of Khafre, researchers claim to have found 8 cylindrical structures arranged in 2 parallel rows, plunging to a depth of 648 meters. These columns appear to merge into 2 massive cubical structures, each with sides measuring around 80 meters. Additionally, the team reported voids and corridors stretching nearly 2 kilometers beneath the plateau. The press announcement sparked intense controversy. Thousands embraced the discovery, while thousands more denounced it. 3 individuals spoke at the press conference. Corrado Malanga, a professor of chemistry from the University of Pisa; Filippo Biondi, an engineer specializing in electrical systems and radar technology, currently a doctoral researcher at the University of Glasgow; and Armando, a veteran journalist with a deep interest in ancient Egypt history. We will focus on Biondi by starting from the very beginning of his history. Filippo was originally an electrical engineer. He later earned a PhD, specializing in radar systems, and has worked in the field for over 30 years. As part of his work, he used a particular type of radar known as synthetic aperture radar, or SAR. This isn't new technology. It's been around since the 60s and 70s. The radar unit can be mounted on an aircraft, a drone, or even a land-based vehicle. But its most common and effective use is aboard satellites, which provide a broader survey range. Here's how it works. SAR uses radio waves, which are sent out, bounce off objects, and then returned to the receiver. The system captures multiple low-resolution images, which are then processed and combined to create a detailed, high-resolution picture. SAR technology has become a powerful tool for tracking environmental changes such as deforestation and desertification. How many square kilometers of forest were cut down and burned in a given year? SAR can answer that. It's also used in military applications, especially in times of war, to monitor troop movements, tank deployments, and crowd mobilizations. Unlike traditional cameras, SAR had a distinct advantage. It works at night, in daylight, and under extreme weather conditions. That's because it relies on the emission of radio or microwave signals, dependent on the time, which can penetrate clouds and atmospheric disturbances. But SAR has one major limitation. When it comes to underground scanning, especially from satellites, its penetration depth is extremely limited. That's because satellites orbit at high altitudes, often around 650 kilometers above the ground. So, if SAR can only scan to shallow depths, and Biondi knows this well, how could he claim to have detected what lies beneath the pyramid? That's where Filippo introduced an entirely new approach. The technique he used was a hybrid system, SAR echography with Doppler imaging. What we want to do here is break it down piece by piece and try to understand exactly what Filippo did. Actually, the system combines three different types of imaging and processing methods. Let's revisit the first one, SAR. As we mentioned earlier, SAR captures multiple low-resolution images, which are then analyzed and merged into a single high-resolution composite. The second and third components, ultrasound imaging and layered reconstruction. The best-known example of this is the 3D ultrasound scan used during pregnancy. This is what actually happens during those scans. A doctor passes a handheld probe over the mother's abdomen. The device emits sound waves from multiple angles. Depending on the speed at which those waves bounce back, it starts to form an image of the fetus. Ultrasound gives us an initial outline, a basic picture of the fetus's position or gender. But the layered reconstruction goes even further. It takes that data to the next level, reconstructing it into a 3D model. You can now see finer details like the baby's facial features, body shape, and so on. Let's try a quick demonstration to simplify this idea. Imagine we have 4 identical metal cups, like this one, and we line them up side by side. Under just one of them, we place a few small wooden blocks. Now, without peeking under the cups, your task is to figure out which one hides the blocks. The simplest method is to start tapping on each cup. The one sitting over empty space will give you off a lighter, more resonant sound. It may confuse you more than help, but the one with the wooden blocks underneath will sound more muffled because the blocks dampen the vibration. The cup over the void will vibrate more freely while the one over solid material won't. Now, let's take this a step further. Let's say you didn't hear a difference in sound. Try something else. Attach a sensor directly to the top of each cup and start tapping again. Next, we will take the audio captured from the taps and feed it into a frequency analysis program. For this demonstration, we're using a free tool called Audacity, but you can use any similar software. We have recorded 4 taps, one for each cup. We select each tap and choose an option called spectrum analysis. This function shows us the frequency distribution within a sound file, helpful for understanding the various frequencies and their intensities. Now, the visual output may seem unfamiliar at first, but it clearly shows the frequency peaks produced by cup number 1. From this chart, we can determine that around 1700 Hz, the signal spikes sharply. This is what we call the dominant frequency, the point where the cup resonates most, and essentially its natural frequency. Now, let's line up the spectrum visuals for all 4 cups side by side. We will notice that all cups exhibit a peak around 1700 Hz, indicating that they all resonate at roughly the same base frequency. However, the intensity of that resonance varies. For cups 1, 3, and 4, the signal intensity is around -12 dB, but cup 2, it's down to about -18 dB, or slightly less. That's a noticeable drop, indicating something is muffling the sound. There is another clue. The echoes or reflected waves in cup 2's data are much weaker, suggesting that something underneath is disrupting or absorbing the sound waves. Putting these 2 observations together, it becomes clear cup 2 is the most likely candidate. Something beneath that cup is scattering the sound and weakening the signal, exactly like the wooden blocks we placed earlier. This tells us that The presence of objects of specific size and density can alter the resultant frequencies, and that sonic readings can reveal things we can't see in the naked eye. If we want to get a clearer idea of what's underneath, we can tap the cup from different angles and measure how fast the sound bounces back. From this, we can begin to map out a 3D shape of whatever is hidden below. Now imagine we had a program that could take all these sound data points and convert them into a three-dimensional model. Let's move on to the third and final part, Doppler imaging. The Doppler effect is a common physical phenomenon we experience almost daily. It refers to the apparent change in frequency due to the relative motion between the source of a sound and the observer. It was first described by Austrian physicist Christian Doppler in the 19th century. Let's break this down with a simple field experiment. We headed out to a quite open area so we wouldn't disturb anyone. We conducted 3 different tests. In the first one, we passed by in a moving car while honking the horn. In the second, the car remained stationary while honking. And in the third, we stood still while the car sped past us at high speed, again using the horn. In scenarios 1 and 2, whether sitting inside the car or standing in front of it, you hear the horn at a steady, unchanging pitch, because you're either moving with the sound or standing right in front of it. But in the third test, the moment the car speeds past you, you hear the signature shift in tone. That's the Doppler effect. This compression makes the pitch sound higher when the car is coming toward you and lower as it moves away. The Doppler effect has quite a few practical uses, thanks to a clear scientific formula that links an object's speed to the frequency of the sound it emits. Doctors, for example, use it to measure the flow and speed of blood through the body. That's why you might hear them say, "You should get a Doppler scan to assess blood circulation." Astronomers also use it to detect the motion of stars, whether they're moving closer or drifting away. And beyond just direction and speed, the Doppler effect is sensitive enough to detect extremely fine movements. One of its modern applications is in new cars. There is a serious issue that sometimes happens. A parent might accidentally leave a sleeping child inside the car. In hot weathers, this can lead to suffocation. So, what does the radar system do? It detects the minute chest movement of a breathing child, even if they're lying behind the seat. Radar can measure movements down to the millimeter, something a camera can't do. Once it detects this, it sends an alert to the driver or even directly to emergency services. We now understand the core technologies that Filippo Biondi used in his study of the pyramids. At the Pyramid of Khafre, located on the Giza Plateau, there is constant hum of environmental noise. Wind striking the stone surfaces, people walking around, cars driving past. All of these produce vibrations that travel deep into the ground, causing echoes and resonance if there are any hollow areas or tunnels beneath. Doppler-based radar is sensitive enough to pick up even the slightest subterranean water movement or subtle tremors, all signs that may point to underground cavities. These sound echoes then bounce back toward the surface of the pyramid. A satellite traveling at 7 kilometers per second and orbiting high above is listening to all of this. It can remotely scan the Giza Plateau over a span of up to 20 years. The satellite sends rapid pulses toward the pyramid, about 100 pulses per second, and records the returning vibrations. Any subtle change in the returning data is treated like an acoustic image. Now, keep in mind, the radar doesn't physically look underground. It doesn't penetrate the Earth in the traditional sense. The signals come back to it naturally, and it simply captures and processes this data. Once collected, these signals are analyzed and rendered into imagery. In most cases, blue areas represent solid, homogeneous material, while red areas indicate voids or zones of high vibration. Using a series of mathematical equations detailed in his published study, Filippo processes this data to calculate the size and depth of cavities beneath the pyramid. The software he developed then converts the processed signals into 3D model, making the underground structures visible. This entire system, this method of remote underground scanning via satellite, is patented in his name as of 2022. It's officially his intellectual property. But why does that matter? Because this technology could completely transform how we conduct archaeological research. If certain environmental conditions are met, it allows us to explore depths of several kilometers remotely from space. And when Filippo applied the system to the Pyramid of Khafre, it produced a shocking revelation. Let's look at some of the other locations where the system was tested before Khafre. In 2016, reports began to surface that the Mosul Dam in Iraq was facing serious structural risks, urgently requiring maintenance. The Iraqi government contracted an Italian company named Trevi Group to carry out the repairs. So they coordinated a detailed study with multiple institutions, including NASA, the University of California, and several German and Italian research centers. One of the key figures in that research team was Filippo Biondi. Their findings were published in the prestigious journal Nature. And from that point on, the monitoring of the Mosul Dam became a continuous effort. By 2020, Filippo had assumed responsibility of all subsequent assessments. In November 2020, he published another study, this time on the Morandi Bridge in Italy, using the same radar-based methodology. He identified structural weaknesses and faults. Earlier that same year, in August 2020, he turned his attention to Mount Vesuvius, employing the technique to probe as deep as 3 kilometers beneath the surface. His aim was to map the volcano's internal structures, analyze vibration patterns, and help forecast future eruptions. In Italy, Vesuvius is more than a geological feature. It's a national concern. An eruption could endanger millions of lives. This made the accuracy and integrity of Filippo's research absolutely critical. The findings could not be speculative. They had to be precise, peer-reviewed, and defensible. Filippo also brought the technology to bear on the Grand Sasso Physics Lab. He successfully mapped its layout and published the results on his official platform. By this point, the technique had not only been field-tested, but also validated and recognized across the scientific community. It was around this time that Corrado Malanga, a chemistry professor with a deep fascination for ancient Egyptian history, approached Filippo. He proposed a new challenge: to apply this groundbreaking technology to Egypt's most iconic structure, the Great Pyramid of Giza. Filippo launched a full-scale project using an Italian radar system known as Cosmos SkyMet, which consists of 4 synchronized radar units. Over the course of 7 months, he conducted 12 separate scans. The acoustic echoes from chambers and voids beneath the surface were captured. Using Doppler imaging, he focused specifically on the fine vibrations produced by hidden rooms and tunnels. Once the data was collected, it was processed using the custom software developed by his team, resulting in detailed 3D reconstructions of the Great Pyramid's interior. The results included a comprehensive map of known and lesser-known internal features: the King's Chamber, the Queen's Chamber, the Grand Gallery, and the Subterranean's Chamber, along with associated passageways, air shafts, and hidden voids. Yet, despite the sophistication of the study, it didn't trigger a major global reaction. Why? Because much of what was revealed had already been reported by another team known as Scan Pyramids. Scan Pyramids is a multinational collaboration involving experts from Egypt, France, Japan, and other countries. Back in 2017, they made headlines after using muon tomography, a technique that measures the path of cosmic particles as they pass through solid structures, to scan the pyramid's interior. Their findings revealed two voids: a large one above the Grand Gallery and a smaller one above the pyramid's entrance. The large cavity was estimated to be no less than 30 meters in length. Filippo's team, on the other hand, measured it at 23 meters. So, which is correct? So far, no expedition has physically accessed the void to verify either claim. As for the smaller cavity, Scan Pyramids did not specify its dimensions, but Filippo's group, publishing in 2022, estimated it to be 15 meters long. Then in February 2023, a camera probe finally entered the space. The actual length? Around 9 meters, meaning both earlier estimates had a margin of error of nearly 40%. Such discrepancies may seem significant, but they are to be expected, considering that these readings were taken from a satellite orbiting at 650 kilometers above Earth. At the very least, he managed to detect something, and that's significant. Especially considering that, unlike Scan Pyramids, he didn't leave his office. No travel to Egypt, no need for permits, no excavation teams, no physical equipment. And yet, he still managed to pinpoint the existence of an underground cavity. This is where the real strength of the technology lies. Filippo's study of the Great Pyramid was published in the journal Remote Sensing in October 2022. Naturally, after completing the scan of the Great Pyramid, the team turned their attention to a new target, the Pyramid of Khafre. Now, equipped with experience from the initial project, they began applying their advanced radar technique beneath Khafre's pyramid. And what they found stunned even them. The scans revealed 8 massive cylindrical structures arranged in parallel rows. These were connected by helical formations, ending in stone cubes nearly 80 meters wide. Below these, additional cubic structures were detected. The subterranean voids beneath the Giza Plateau extended for nearly 2 kilometers, right beneath the pyramids. Moreover, the scans revealed repeating void patterns surrounding the main chambers of the Pyramid of Khafre. The team was completely astonished. Armando, Filippo's colleague on the project, couldn't believe the results. He initially dismissed them as interference, just background noise, he said. He warned the data might not be reliable. But the very next day, they ran a second scan. Same result. Third day, same result. A week later, still the same results. To rule out any chance of error, they brought in 2 independent satellite systems from the United States, Capella Space and Umbra Space. Over the course of an entire year, both companies returned identical readings. Filippo and his team compiled nearly 200 layered imaging reconstructions, known as demographics, each taken from a different angle. These images were then merged and processed, resulting in a consistent multi-angle 3D model of what lay beneath the pyramid. But what truly baffled the team more than anything else were the spiral structures. Their unusual geometry demanded a closer look. To ensure the results were accurate, the team turned to a method called calibration, which involves comparing new findings to a known similar structure. So, where did they find such a comparison? It was in Italy, at a well of St. Patrick. This historic structure is approximately 23 meters deep and 33 meters wide, and features a spiral staircase, exactly the characteristics they needed for comparison. When Filippo's team scanned the well, they found that the helical attributes matched those observed beneath the Pyramid of Khafre. This finding gave Filippo the confidence to speak more firmly in interviews that followed. Responding to critics who dismissed the anomalies as natural voids, he said, "I reject that interpretation. These are not characteristics of natural formations. We're talking about right angles, repeating stone cubes, multiple spiral structures, and precise linear carvings. These features suggest intentional design. They are man-made, not geological." Filippo concluded that what they had found beneath the Giza Plateau was an engineered structure sculpted by human hands deep within the bedrock. The 3D models revealed enormous structures with shapes that defied conventional expectations. They looked less natural formations and more like mechanical components, as if the second pyramid were, quite literally, a massive stone machine. That's when the backlash began. Despite the fact that the only thing revealed was a 3D rendering of voids, the scale and familiar geometry sparked a storm of criticism. One of the challenges facing this discovery was the media narrative that quickly formed around it. Terms like a city beneath the pyramid or underground pillars began circulating in headlines, labels that were never used by Filippo's team. Instead, he was precise in his language. He referred to them simply as structures or architectural forms. That distinction matters. It wouldn't make any sense to hollow out the ground beneath just to install some sort of support columns. If those voids existed from the start, then what purpose might they serve? The spiral structures, for instance, could very well be staircases, like the one we saw at the well of St. Patrick, or they could simply be spiral excavation lines waiting for the confirmation. We have a theory about what this discovery might represent, but it remains incomplete. Still, it opens the door to broader implications, such as the long speculated theory of pyramidal energy transmissions. Some believe energy was generated beneath the middle pyramid through seismic vibrations, which were then received and amplified by the structure above. The idea of pyramids being built over underground tunnels or structures is in fact not new. The step pyramid of Djoser was constructed directly above a vast subterranean complex. The Pyramid of Abu Ruash is situated atop an ancient vertical shaft. The Osiris shaft beneath the Giza Plateau reveals a bizarre arrangement of carved features, and the plateau itself is riddled with a visible network of tunnels, easily observed by anyone walking the area today. The problem is, we were born into this reality, so we've grown used to it. We no longer question the idea that these pyramids were built with primitive tools and simple methods. But in a recent interview, Biondi dropped a bombshell. He claimed that all three pyramids at Giza are built above similar underground structures. However, the team has only revealed one so far. I understand how this might sound far-fetched. It's enough to give anyone a headache. But what if all three pyramids are connected by a single corridor? Keep in mind that for every 20 meters you go underground, the temperature typically rises by about 1 degree. So, at a depth of 700 meters, we're looking at a temperature increase of at least 30 to 40 degrees Celsius above surface level. Now, add to that the complete lack of ventilation and the high humidity due to underground water. So, what kind of tools could possibly operate under such extreme conditions? Whether this discovery is definitely proven or not in the future, one thing is certain. There are powerful vibrations occurring beneath the Giza Plateau. These vibrations are the result of groundwater activity and the unique structural design of what lies below. And one of the clearest indicators of this is the massive size of the pyramid stones and their seemingly impossible constructions. Look at the interlocking system used in the surface structures. It's no accident. This design appears engineered to transfer underground vibrations upward while protecting the integrity of the pyramids. In the lower levels of the Pyramid of Khafre, individual blocks weigh 50 to 60 tons. In the Khafre Valley Temple, some stones weigh up to 400 tons. The same applies to the Temple of the Pyramid of Khafre. Such colossal weights would be unnecessary if these structures were merely funerary temples. Their real purpose, it seems, was to absorb and withstand deep seismic activity beneath the plateau. In fact, the Giza Plateau itself appears reinforced at its edges with giant stone blocks, as if extending or buttressing the ground around the pyramids. Which brings us back to a crucial point. This entire system was designed this way from the very beginning, and water appears to play a central role in how it all works.
We found the same structures below each pyramid. We have to consider the Giza like something connected, so all the plateau. No? Water can have a crucial role in this business, so the Giza Plateau.
When the announcement was first made, it drew a massive crowd of journalists and researchers. But because no academic paper was published alongside the press conference, as is standard in such major revelations, this led to even more speculation and confusion. There was no centralized source of information, and that, in my opinion, is a valid criticism of the team. The announcement wasn't handled properly, especially for a discovery of this magnitude. However, let's be clear. The poorly managed announcement doesn't mean the entire discovery is invalid. As we mentioned, the core idea had already been published across 4 prior studies. And according to the lead researcher, we only publish again if there is something new in the technique itself. If the method remains the same, then there is no need to republish. He emphasized that anyone with a solid understanding of SAR could follow the steps already laid out and arrive at the same findings. That said, he also confirmed that a paper on the Khafre pyramid will likely be published in the coming months, although it won't contain any new information beyond what was already shared at the press conference. Unfortunately, the backlash was swift and fierce, particularly from academic circles in archaeology. Accusations of fabrication and pseudoscience quickly followed. Many rushed to criticize the findings, often without even understanding the technology involved. This reminds me of a historical parallel. Back in 1912, a German meteorologist named Alfred Wegener proposed a bizarre idea. He claimed that all the continents we see today were once a single landmass, which over time drifted apart into their current positions. This was the birth of what we now call the continental drift theory. Part of its evidence was how the coastlines of Africa and South America fit together like puzzle pieces, and how identical fossils of ancient animals and plants were found on both continents. He published his theory in a 1915 book titled The Origin of Continents and Oceans. At the time, the idea was mocked. Critics said, "Nice theory, but you haven't explained how the continents actually moved." One of the most vocal skeptics was Sir Harold Jeffreys, a renowned British geophysicist, who argued that continental movement was physically impossible without an immense external force. But then, in the 1960s, the theory of plate tectonics emerged, and suddenly the scientific world realized Wegener was right all along. He simply didn't have the tools at the time to prove it. When asked in a recent interview how confident he was about the findings beneath Khafre's pyramid, Biondi said he was 90% certain of their accuracy. In fact, it's likely that in the coming months, other researchers will repeat the measurements around Khafre's pyramid, and at that point, the findings will either be confirmed or disproven. Personally, I would have hoped that Egypt's Ministry of Antiquities would have reached out and said, "Let's work together to verify or debunk your results," especially since this researcher has published and proven aspects of his technology in the past. It's a tested, recognized method. Right now, though, the Italian team is working independently. They have stated that their plan is to scan the entire Giza Plateau, then move on to Saqqara, the Lost Labyrinth of Hawara, the Osirian in Abydos, and possibly even the Valley of the Kings. This is without question a golden opportunity, one we hoped is seized wisely. I'm not claiming I fully understand the technical or mathematical details of the radar process just yet. That would take time. I'm also not telling you to believe it or dismiss it outright. What I'm saying is this: take your time, investigate, search for the truth. Because regardless of where this leads, this moment could be one of the most pivotal turning points in the modern study of the pyramids and the true history of ancient Egypt.